Hello and welcome back to High Peak Education. In previous videos I've discussed rotational motion and the fact that there must be a centripetal force. And I've discussed that this centripetal force arises due to the fact that the object is changing direction. So anytime an object is on a curve, it has a centripetal component to it. So I'd like to go into some more detail here by showing an example of a carousel. So I'd like to thank Professor Walter Fend once again for these wonderful animations and simulations that you can get online. So what we have here is we have a carousel shown, and the idea is that in the absence of air resistance, we can instantly change this carousel in terms of its period, that's the time it takes to go round, its distance between suspensions and the axis of rotation, so that's the distance between each of these objects and the central rotation axis here. We can also change the length of the strings, and we can also change the mass of the objects. So we'll be changing each of these one at a time. And I'll be describing what's going on. So this is a model of centripetal force, and it really demonstrates to us via vectors and via forces and via free body diagrams what an actual centripetal force, that is a net force, actually looks like. So let's discuss this. Here we can see the carousel, and notice that I can really identify that there are two forces on these objects. In the absence of air resistance, we should have a tension force and a weight force. That is the tension force that goes up these strings, and then a weight force that pulls the object down. By the way, let's assume that these cords are very, very thin, so let's ignore the mass of those cords. That way we don't have to worry about the weight force of those cords directly. What should the forces look like when we click on this radio bullet showing the carousel moving around with the force vectors? Okay, stop and pause the video if you need to before you go ahead and see what I show, because it's a good idea to predict before just seeing. Okay, so notice that the tension forces are shown in blue, the weight forces are shown in black. So the tension forces go straight up the cord, so they're canted at the same angle as the geometry of the cord themselves. The weight forces are straight down toward the center of the earth, but notice that the force that is unbalanced, that is the net force, in other words, the component of the tension that's towards the axis of rotation, is shown for you here in red. And those red vectors are manifesting the net force, which is the centripetal force. Now listen to me for a second. Net force is the unbalanced force. It's not a separate kind of force. There's no such thing as a kind of centripetal force. But the tension force horizontal component is manifesting itself as the centripetal force. Let's have a look at that via a sketch of a single mass when it's stopped and examined on an axis in a plane. So look what we have here. We have a tension force going up the cord. We have a weight force going down. The vertical component, you could call that maybe the y component of the tension, balances the weight. But notice that the x component, that's the horizontal component, of the tension force exactly equals the net force, the centripetal force. So that's what holds the object toward the center. Okay? The nice thing is here we can actually look at the numerical values. So remember we said the period, that's the time it takes for one full rotation. So if you watch the animation, one full rotation took 4 seconds. That is a frequency of 0.250 hertz, 1/4 of a hertz. Why is that? Well, if it takes 4 seconds for one rotation, we only complete 1/4 of a rotation. In other words, 1/4 of the repeat every 1 second, because hertz is cycles per second. So it's a quarter cycle, in other words, a quarter turn every 1 second. Notice what the angular velocity is, 1.57 radians per second. To me that sounds like pi divided by 2 radians per second. But that should make sense to you, because we go through 2 pi radians every 4 seconds, so that's going to be pi radians every 2 seconds. So that's about 1.57 radians per second. By the way, we're assuming uniform circular motion here. What about the velocity? The velocity here is the tangential velocity, and that should be the angular velocity times the radius. Now notice the radius here ends up being 1.31 meters. Now the question is, how do we get that? Well, we'd have to work out the geometry. If you go back to this sketch, remember this distance from the axis of rotation to straight down, that is to straight below if the object was not rotating, that was exactly 1 meter. We're also assuming the length of this chord is 1 meter. Those values are set over here. But also notice that because we rotate, the object cants out. Why does it cant out? Because we need a tension force that's in the horizontal direction to create that centripetal force, to create that net force. So if we take the angular velocity multiplied by the radius, we should get the linear velocity, or the tangential velocity. Looks like this angle is about 18.3 degrees. You could get that a few ways. You could say, well, this angle is the x component of the tension, and that x component of the tension is say the opposite side, and then the adjacent side of this right triangle would, let's say, be 1 meter. Okay? And notice that to get this adjacent side, that's geometric, whereas this horizontal side, that's force, what I already mentioned. But you could figure out the geometry of this. You could figure out if this is 0.31 meters and this is 1 meter, then the tangent of theta, the tangent of 18.3 degrees, should equal that ratio. Furthermore, you could also find the angle theta if you knew what, let's say, the y component and the x component of the tension were, and you could set the y component of the tension equal to the weight, and you could set the x component of the tension equal to the centripetal force, which we know to be like either mv squared over r if we're performing this with linear velocity, or m omega squared times r. That's mass times angular velocity squared times radius. Going on down from here, if it's a 1 kilogram mass, the weight should be about 9.8, or more exactly 9.81 newtons. The centripetal force is going to be, again, mv squared over r. So if you take this velocity squared, 2.06 meters per second squared, times by 1, and then divide by this radius of 1.31 meters, I guarantee you'll get 3.24 newtons. And thus the tension in the string is 10.3 newtons. And notice that's going to be the Pythagorean sum. In other words, that's going to be the weight force squared plus the centripetal force squared square rooted. How do I know that? Because the centripetal force is equal to the x component of the tension. The weight force is equal to the y component of the tension. So if we do weight force squared plus centripetal force squared and take the square root, we should get the tension force, which is this total force. Okay? So that's kind of the idea. Now, let's go on from there and let's make some changes. So now, let us have the period. So if we have the period, I think the frequency should be twice as much. And if we have the period, I think that instead of taking 4 seconds for an object to move around and make 1 full revolution, I think the object's going to make that same revolution in 2 seconds. So, that being the case, we should take a look at what happens to the frequency and these other things. Also, given that the period is going to be shorter, it's going to be 2 seconds, I think the angular velocity is going to be twice as much. Because again, it's uniform circular motion, and we should go the same circumference distance in half the time. So I think the angular velocity will be twice. But if the angular velocity is doubled, I think the centripetal force will be 4 times as much. Because if it's m omega squared times r, now by the way, the r will actually be increased, so we'll have to think about it, but the centripetal force will definitely be larger. Okay? So keep your eye on these numerical values, and we'll come back to those. And then let's keep the mass the same, and let's keep the distance from the suspensions to the axis and the length of the string the same. Okay. So let's go ahead and change this to 2.0 seconds, 2.00 seconds for the period, and let's hit enter and see how things are different. Look at that. Notice that the angle is also larger, you notice. That is the angle from vertical. Let's think about why this is. If the centripetal force is larger, I think that the tension force needs to be larger. Why? Because the tension force in terms of its horizontal component is causing these objects to change direction. In other words, have a centripetal force. And the idea is that the faster we go, the shorter the period, and the shorter the period and the faster we go, the larger the tension force and the larger the centripetal force required. Okay? So the angle should be greater because we need a larger centripetal force. So let's show those forces. Notice, compared to what we had originally, the weight force is still exactly the same. It's still 9.81 newtons. Okay? Those of you that have heard me do problems before in earlier videos, I typically just use 9.8 for the gravitation constant. So a 1 kilogram mass would be about 9.8 newtons, but 9.81 is just a little more exact, near the surface of the Earth. So that has not changed. But given that the angle has grown, the only way for us to balance that vertical component of the weight force is to make the tension force quite a bit larger. Now look at these tension forces. These blue vectors are quite large, headed up towards the top of the axis of rotation. Notice the x component, which would be the horizontal component, you might call that the radial component, of the tension force that's directed inward toward the axis of rotation is now quite large. Now, if there was no change in radius, we'd expect a doubling, because the period was half, the angular velocity was twice. You square a doubling factor in m omega squared r, you get 4 times the centripetal force. But we'll have to investigate what else actually happens. So let's look at the sketch. Notice the sketch is indeed quite a bit different. The weight force is the same, but again, the angle is larger, the tension force is certainly larger, and thus the net force that results, that's unbalanced, is larger. Let's look at the numerical values. The frequency is indeed half. The angular velocity is indeed double. Notice also the radius is larger, okay? Because since the angle is increased, we're further from the axis of rotation. Look at the linear velocity. The linear velocity is angular velocity times radius. That's also definitely quite a bit larger. Now look at the angle. It's 62.2 degrees. So the weight force is still the same. The centripetal force is like so, 18.6 newtons. Now if I quickly go back to 4.00 seconds for the period, notice the centripetal force has gone up substantially. And notice it's even, I think, it's more than 4 times. So in fact, we can verify this using the calculator. When the period is 2.00 seconds and the centripetal force is 18.6 newtons, compare that to a period of 4.00 seconds and the centripetal force being 3.24 newtons. Let's look at this calculation. 18.6 divided by 3.24, approximated to 3 decimal places, is about 5.74 times larger centripetal force. Remember, since the object not only doubled its angular velocity but increased its radius, it's going to be more than 4 times the centripetal force. So it's about 5.74 times. Okay, so this is what we mean. Now, notice the tension in the string is 10.3 newtons. Previously, and that's with a period of 4 seconds, but with a period of 2.00 seconds, it's 21.0 newtons. So let's try this calculation. So let's go alpha F1, numerator over denominator. So let's try 21.0 divided by, and again, previously we had 10.3 newtons. So this is a little bit more than twice the tension force. A little bit more than twice. And again, it's because we have twice the angular velocity, so the tension force gets quite a bit larger. Okay, so this is what we saw with the sketch when we compared 4.00 seconds and now 2.00 seconds for the period. We noticed that, again, the centripetal force and the tension are quite larger. Okay, so this is what we mean. Now let's go back to our original experiment of 4.00 seconds. So now that we've made modifications with the period and we think we understand centripetal force, now let's change the distance between the suspensions and the axis of rotation. So these suspensions are sort of tied in here, a certain distance outward, 1 meter, that's our basis here, from the axis of rotation. Okay, so we're going to make the suspensions closer to the axis of rotation. So let's do 0.5 meters, okay, and see if you see anything looks really different. Okay, well, it looks to me that the strings are closer to the axis of rotation, okay, and we note that the motion looks a little different, but not extremely different, because the period is the same. That's the time it takes to go around. So the frequency should be the same. So the angular velocity should be the same. So that should be the same as long as the period does not change for any of the rest of these experiments. But let's compare the forces to what we had before we decreased the distance between the suspensions and the axis of rotation. Notice here it looks to me that the centripetal force is a little bit larger, and then to me when we go to 0.5 meters between the suspensions and the axis of rotation, looks a little bit smaller. Okay, now the weight has not changed. That's because the mass is the same. But notice that the angle is certainly less. Why is that? Because since we're closer to the axis of rotation, the tension force can be more so straight up, and that's more so basically balancing the weight, and the centripetal force is probably a little smaller. Let's go ahead and look at the sketch. Okay, this does look to be the case. Even though the angular velocity, the period, and the frequency are the same, period is 4 seconds, the frequency should be 1/4 of a hertz, and then the angular velocity should be pi over 2, or 1.57 approximately, radians per second. Let's go ahead and look at the numerical values. So notice the frequency and angular velocity have not changed. The radius is certainly less because we're not as far out from the axis of rotation. The tangential velocity is less because the angular velocity is the same but the radius is smaller. So we're not moving as fast of a linear speed. Look at the angle. It is indeed less. The weight is not changed. The centripetal force is less and the tension in the string is less. And if you don't believe me, let me return to the 1.00 value. Notice these were our basis values of radius, velocity, that's tangential velocity, angle, weight, centripetal force, and tension in the string. When we go to 0.5, the distance between the suspensions and the axis of rotation, notice the things that I mentioned that do change, do indeed change here on the numbers. Okay, So let's go back to our basis of, again, 1 meter between the suspensions and the axis of rotation. Now let us change the length of the string. Let's make the string shorter. Again, you should think about what's going to happen. So certainly the strings we can just see are shorter. It's difficult to see, but I believe that the angle itself does change and the forces do change, ever so slightly. Now again, because the period doesn't change, the angular velocity or the frequency shouldn't change. Okay? But when we look at the forces, now it looks like indeed the centripetal force is a little bit less. Why is that? Well, let's examine it side by side. There's 1 meter length of string, and then let's change that again back to 0.5. You see that it is different. Now the weight certainly has not changed because the mass is still the same. Let's look at the sketch. So indeed it looks like it is a little smaller centripetal force. Remember, the centripetal force is the net force. That's the radial component of the tension force here. Let's go back to 1.00 meters. So you can see it looks like it is a little different, and the angle looks to be a little different to me as well. Let's look at the numerical values. So look at this. Instead of the angle being 18.3 degrees, now it's 16 degrees. Whereas the centripetal force is also a little bit smaller than it was when we had 1.0 for the length of the string. Weight hasn't changed. Angular velocity and frequency are the same. The radius is certainly smaller. Okay? Because the radius is smaller, the linear or the tangential velocity is smaller. Weight is staying the same. But notice, because the linear velocity is smaller, I think the centripetal force should be less if we were at the same radius. But again, the radius has actually gotten smaller, so if the angular velocity stays the same, but the radius is smaller, then by m omega squared r, the centripetal force should get smaller. And if the centripetal force gets smaller, the tension is less. And if the tension is less, to support the same weight force, you don't need as large of an angle. So the centripetal force is indeed less. Let's return to our basis experiment and let's do the last thing. And the last thing here is going to be if we change the mass. So what happens if we change the mass? Well, the mass should affect the weight. Okay? So let's put the forces on here and let's see what happens when we increase the mass. Now, by the way, I think the angular velocity should stay the same, and the period should stay the same, and the length should stay the same. So I think the geometry all stays the same, including even the rate of rotation and so on. But I think the length of the force vector should change. And that's because if we have more mass, we have more weight, greater tension force, greater centripetal force, and by m omega squared times r for centripetal force, which is the net force, m gets doubled, then the radius stays the same. We should double the centripetal force. So 2.00 kilograms. Okay? So notice that what actually changed was this sort of force vector here. Okay? So 10 newtons is now quite a bit smaller, and indeed they actually did go up. Now, it's hard to see, but keep your eye on this 10 Newton vector and see what happens if I slowly increase the mass. Let's go 1.2. Okay. Let's now go 1.4. Okay. So those things are changing. Let's look at the sketch. So in the sketch, if we increase the mass to 2.00 kilograms, okay, again, the geometry stays exactly the same, but this vector is now just worth more. Basically, our basis axis vector has changed. Let's look at the numerical values. Notice at 1.00 newtons, the tension was 10.3 newtons. Now when we go to 2.00 kilograms, the tension is a little bit more than double. It's about 20.7 newtons. Look, the angle, the linear velocity, the radius, the angular velocity, and the frequency, they've all stayed the same. But the weight is double, and notice the centripetal force. So the centripetal force should be about double. So that's exactly what we mean. Okay? So this is how we model things for modifying centripetal force, free body diagrams, changing properties of rotation, and so on. So thank you very much for watching this video, and thank you for supporting High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks. Please comment on the video. I look forward to seeing your comments, and I will see you in the next video.